Welcome back. We're going to continue our discussion on titrations and buffer. And as you could see, I've written 4 different chemical reactions involving acids and bases, and each are unique in their own aspect. And we're going to draw 4 qualitative pH graph. Yes, I said qualitative, meaning we're not going to do any calculations. We are going to qualitatively construct graphs which are not going to be drawn to scale. All right, with that said, let's look at the first reaction. We have sulfuric acid, which is a strong acid. Now, if you remember a list of strong acids and base gave, this was on it. And I said anything with OH and first group and second group metal is a strong base. So essentially we have a strong acid, strong base, and it's going to always, any acid base always results in the formation of salt and water. Okay. Okay, now another thing that's very important here is first you have to identify what type of acid and base you have. And the second thing is the acid monoprotic, diprotic, or polyprotic? In this case, it is diprotic, right? That's very important because we have not discussed this unique aspect of it in the previous video. So let's go draw our scale. So this is our pH, which is our y-axis. And where acids listed first, base is second. So acid goes in the flask, right? And then the sodium hydroxide goes in the burette, right? Sorry for my bad drawing. That's you should say that's burette. All right. So that means volume of base added, right? It's milliliters. Good. Okay. Now, if the reason is when your acid is monoprotic, whether it's strong or weak, it doesn't matter. You have only one inflection point. When your acid is diprotic, you got 2 inflection points. What do I mean by that? You'll see in just a second. So here's the first and second. You see, it looks like a giant snake that's curled up, right? So you got the first inflection point and second inflection point. We don't need to be accurate. Again, we're saying that this is where the pH first is and second here is. The middle portion of the flat is the pH, right? So we are going to say that this got 2, so this is sulfuric acid, right? So if you have 2 hydrogens, you will have 2 inflection points. If you have 3 hydrogens, then you have 3 inflection points, all right? But another thing you have to pay attention to is we're adding base to an acid, so our direction should be from the base to the top, that is bottom up, okay? We're going from lower pH to higher pH, okay? Again, we are not particularly doing any math here. We're just drawing a bunch of graphs. All right, so this is 0 and somewhere is 7, somewhere is 14. This is just to complete the graph. All right, let's moving on second. Again, this is a strong acid and this is a strong base. Acid is listed first, so that's going to go in the conical flask, and then the base is listed second, so it's going to go in the burette. So graph might look something like this. This is pH again. Y-axis is always pH, 0, 7, 14. I might switch color after these two because I don't want too many reds here. All right, so again, we're adding base into an acid, so volume of base is on the, because people can trick you with this graph by just changing the x-axis, but the graph and everything else might look perfectly. Again, we're adding base to an acid, so we have a bottom-up approach. That means we're going from lower pH to a higher pH. And we have a monoprotic acid, which means we have only one inflection point. So the inflection point has to be really big. And if you take the middle portion of it, it should be somewhere around 7, which is right about here, which makes sense. Whenever, for a diprotic acid, the pH is not equal to 7 at any point of time because it's split. But for a monoprotic acid, pH equals 7 at equals point. So a monoprotic acid has one equals point. This has two equals point. This is an equals point. This is an equals point. So it's got two. It's important you pay attention to these details. And then I'm going to switch color now because it's getting too many reds here. Let's switch to maybe blue. Okay. All right. So this is a weak acid. This is a strong base. Okay. So our inflection point is not going to be small, but it's still going to be a bottoms-up approach because we're adding base into an acid. So this goes in the conical flask. This goes in the burette, right? All right, so let's draw the graph. I don't know if I'll have space for the other one. I am going to try to squeeze it here, okay? Actually, I might have room. So pH, I might do it parallelly so that for the next one, okay? So we are again adding base into an acid. So volume of base is the x-axis and milliliters. It's bottoms up approach. Now keep in mind, it's a triprotic acid. That means we will have 3 inflection points, that is 3 equivalence points. So 1, 2, 3, right? I didn't do a very good job. You get the idea, right? As you get more and more closer to the top, you know, accidentally I did the right thing, because as you get more and more to the top, the inflection point becomes less and less separated, like very unique, you know. So this is the first, this is the second, and this is the third. All of these 3 corresponds to equals point. So there's 3 equals point. Okay. So let's complete it. So 0, 7, and 14. That's a weak acid strong base, but nevertheless, it's got 3 inflection points. Let's complete it with one more and a different color. I'm just going to go with this purple. It's good. Okay. So last one. This is a weak base. It doesn't have the sodium or potassium, so obviously it's weak base. This is a strong acid. So this is in the conical flask, and the acid is in the burette. We can do this lab just for you to see how things work. So I'm going to draw this in the minimum of the space I have left. So that's why I didn't do the full screen mode, because too many reds will confuse you. So it's 14, 7, and 0. Here, very, very important, volume of acid, because that's what we're adding. Okay. And as I said, if it's a weak base versus strong acid, the equivalence point pH is below 7. So it should be like this. And if you notice, this is the flattest portion. And if you take the middle of this, then it should be here, which is less than 7. So pH is less than 7. So if it's a weak acid versus strong base, pH would be above 7. Strong acid versus strong base, pH equals 7. This is something you just have to remember by qualitatively remembering it. There is nothing hard about this. So this is not Lowry-Bronsted. This is Arrhenius, something we did when we first, among the theories we did, this was the first one. Because anything acid contains hydrogen, anything base contains OH. It's just that simple, okay? This is an exception. Ammonia is an exception, but that's the way it works. So this is how you qualitatively construct a titration graph. When you actually do a real experiment, you can construct these graphs in the lab, which we would probably do in one of these days. All right, so stay tuned for a pop quiz type of a video where I'm going to have you put these graphs in the respective boxes based on the information provided. All right, so stay tuned.